Hi everyone, welcome back. Today we are going to move on to lecture 5. So today we'll discuss a few theorems. So far done Maxwell's equations, then we did constitutive relations, wave matter interactions, boundary conditions, and the last time we looked at electromagnetic tools, so the different tools that we'll use later. But today we'll kind of continue in that same philosophy and develop some stronger theorems that will be very useful to us. So we're kind of laying the foundation now, and in the next lecture onwards, we'll start actually solving Maxwell's equations. So it's important to kind of lay a good foundation, right? So that's what we're going to do today. So we'll discuss three different theorems and start with what is called Poynting theorem, which relates to power flow. So we all know that electromagnetic waves carry power, energy with them, and we know that because, of course, the sun is putting out light, and that light is propagating through space and then reaches us, and we get energy from the sun, right? So clearly they carry some energy with them, and we want to see how exactly we can model that power transfer. Okay, and that's what Poynting theorem does. Okay, so we start with the scenario like this. We have some volume V and some surface area S. Inside this volume, there are material parameters epsilon, mu, and sigma. And there are also some currents. So maybe this is Js or J rather than Js. So this is some J, and we also have Jm. Okay, so these are the impressed currents or the source currents that provide energy into this system. Okay. All right. So we assume that V is homogeneous, and we start with Faraday's law. So this is the upgraded one with magnetic currents. And we also have modified Ampere's law. Okay, so I kind of removed the component of J, which is the conduction current, because this is an induced current that is induced by the sources, in which case J and Jm are nothing but just the impressed currents. Okay, so we can label this as Faraday's law, and this is modified Ampere's law. Okay, so then what we'll do is we'll do E dot product with Ampere's law minus H dotted with Faraday's law. And that gives us on the left-hand side E dot curl of H minus H dot curl of E. Okay, and on the right-hand side you get E dot D over dt plus sigma E dot E plus E dot J plus H dot dB over dt plus H dot J. Okay. Right, so we have vector identities. So one vector identity says that this is nothing but the divergence of E cross H on the left-hand side. Okay, so we can move that to the right-hand side and rearrange some of these terms. Actually, there's one more thing that we can do. So I can write E dot d over dt as, since it's homogeneous and medium is, your d is given by epsilon E, I can write this as epsilon E dot dE over dt. And that is nothing but epsilon over 2 times d dt of E dot E. Right? Because you can use the product rule, and then you will get two terms that are the same as this. So you need the 1/2 because of that. Okay. So this basically is this plus again this. So hopefully that's clear. Okay. All right. So given that, we can rearrange the terms again. So let me put this in a box. All right. So we send that divergence of E cross H to the right hand side, and we end up with divergence of E cross H plus 1/2 d dt of epsilon mod E square plus mu mod X square plus sigma mod E square. So of course, these all have the vectors on them, is equal to minus j dot E minus jm dot h. Okay. So now whenever you see divergence, you would like to apply the divergence theorem, right? So that's what we'll do next. So we do a volume integral on both sides and apply the divergence theorem. Okay. So when you apply divergence theorem, you get a surface integral, right? So you get nothing but surface integral of E cross H dot ds plus d dt volume integral of epsilon over 2 mod E square plus mu over 2 mod H square dv plus volume integral sigma mod E square dv, and the right hand side is equal to minus volume integral of j dot E dv minus volume integral of jm dot h dv. Okay, and this is essentially Poynting's theorem. So we need to interpret these terms, all of these terms. So let's do that. Okay, so I'm not going to be very rigorous here, but hopefully you have done some circuits in the past, so we'll just use analogies to try and understand what these terms are, but you can derive them rigorously as well. Okay, so maybe we can start with the left-hand side, or let's do the right-hand side. Okay, so this has units of volts times ampere, right? Because J is ampere per meter square, E is volts per meter, and you have an integral over a volume, so you get volts times amperes. And we know that this is nothing but, this is something like writing the inner product of V and I, right? And we know that that corresponds to the amount of power that is supplied by a given source. And this also turns out to be the same, is V times I. So both of them are the power supplied by the sources J and Jm. Okay, you can think of J as a current source and Jm as a voltage source, in terms of analogies at least. Okay, so that's why you have two different sources, and you have two powers being supplied from the right-hand side. Okay, and when J dot E when J is a power supplied, J dot E is negative, so the whole right-hand side is positive. Okay, so just keep that in mind. Okay, so then we go to the other side. What does this look like? So this looks something like V square over R, right? And that's the amount of power that is dissipated in a resistor of resistance R. Sigma here is nothing but 1 over rho, which is where rho is the resistivity. So this is the amount of power that is dissipated in the conductance of the medium. Okay, so it's heat dissipation essentially. Okay, Then if you look on this side, this looks like, maybe I should make some space. Let's move this a bit down. So this looks like 1/2 CV square. This looks something like 1/2 Li square, right? And those are the energies that are stored in the electric and magnetic fields. Epsilon is something like capacitance per unit length. Mu is something like inductance per unit length, right? The units, in fact, are Henry per meter and Farad per meter. So that's what those are. So this essentially, this term is the amount of energy stored in the electric and magnetic fields in that medium. And the derivative of that is the amount of power that is in that medium, right? And power is the time derivative of the energy. Okay, so this is the last remaining term which we will interpret. So what is this saying? This is basically saying that you have some power supplied on the right? Some of that power is going to the loss in the medium, so it's converted to heat. Some of that power is being used to increase the energy in the medium, right? And then this is the last term. So what does this term mean? So since it's a surface integral, you're kind of looking at how much power or some quantity on the surface of that medium, and we know that this has to have the units of power per unit meter square, right? So the only reasonable way to interpret this is to say that S vector, which we will define as E cross H, is the amount of power flowing through the surface per unit area. This is the power flow per unit area along n hat, where n hat is the unit vector of that patch of area that you've chosen. Right? So essentially saying you take a patch of area, it has some normal component. You calculate how much power is flowing through this. You take the limit as this area goes to 0. And that will be a constant quantity, and you can assign that as the amount of power flowing through this point. Okay, and that's what is known as the Poynting vector. And this Poynting vector is essentially carrying power away from the surface. So now we can clearly interpret even this one, right? So since this is a surface integral, this is saying how much power is leaving that surface. So there is some power being generated inside. Some of that is being dissipated. Some of that is being used to increase the energy inside the medium. And the rest of it is leaving the medium. Right? So that's the amount of power flowing outside, from inside to the outside. Okay? All right. So HFSS actually uses this to calculate antenna efficiency, which we'll do later. So power radiated is nothing but the closed surface integral of E cross H. And your first CAD assignment will be on this. So, HFSS usually has some antenna, and then there's an air box around it. And then you have a port assignment somewhere here. And that port, let's say, is 1 watt, is the amount of power supplied. So this you can say power supplied. And then you want to see how much power is radiated, which is given by this integral on the left. So power radiated. And the total efficiency or antenna efficiency is given by P radiated divided by P supplied. This is the antenna efficiency. There's also something called radiation efficiency, which you will see in your assignment. It's slightly different. So that also accounts for reflections at the port as well. Okay, so you'll actually compute this. You'll extract the fields on a given closed surface around your antenna. You'll calculate this radiation power radiated, and you'll calculate this efficiency, and then you'll compare with what HFSS gives you. Of course, HFSS already gives you this value. You don't have to actually compute it like this, but it's nice to see where that comes from and to get that kind of intuition, right? So, okay. So that's about Poynting's theorem or Poynting theorem. It's very useful. It's not obvious actually for a given problem that power flows in this weird thing called E cross H. But in the homework as well, you'll see an interesting problem where um, you'll see that, okay, E and H makes sense, but the power, the way it's flowing is not that obvious always. Okay. All right. So the next theorem we're going to look at is very important. It's called uniqueness theorem. This actually lays the foundation for a lot of things we will do. So it's very important to understand what it is. Okay, so again, we start with some region, abstract. So volume V, surface, then surface S, bounding surface S. And we say there are some currents again inside this, J and Jm. Okay. So what does uniqueness say? It says, given a region, let's write it out. V comma S with sources J comma Jm. Right, the solution to Maxwell's equations is unique in V under the following conditions. So the conditions, so the first condition is that E and H are known everywhere V at some time t equal to 0. And the second condition is that E or H, we should actually say tangential components. So E tangential or H tangential are known on the surface S at any time t. So this is essentially an initial condition, and this is a boundary condition. Okay, so what do I mean by known? So what we're trying to establish is that you have some sources and you have some volume. We're trying to say, okay, given a set of sources, how many solutions can exist in that medium? Okay, and we're saying that, okay, given a set of sources, you can only have one solution in this medium. And that is under the conditions that at some time t equal to 0, you knew what the fields were everywhere. And at all times, you know what the tangential component of E or H is. So if you may know on this region, you know what E tangential is, and on this other region, you may know what H tangential is. You don't need to know both everywhere. Okay, so as long as you know the tangential fields, you can say that you can determine what the interior fields are everywhere, of course, under the initial condition assumption. Okay, so by known, I'm saying that these are in fact unique. Okay, so another way to say this is that you could say that this is unique instead. Okay, so E and H are unique everywhere in V at some time t equal to 0, and E tangential and H tangential are unique on the surface S at any time t. So these are the conditions under which the fields inside are unique. Okay, so kind of an elegant proof. So let's go through it. Okay. So you start by saying that there are two solutions to Maxwell's equations. So solutions So this is something like a proof by contradiction. Okay. So I'm saying, okay, given a set of sources, there are in fact two solutions to Maxwell's equations, E2, H2. Okay. And then we'll define E tilde as E1 minus E2 and H tilde as H1 minus H2. Okay. So we know that by superposition, E tilde and H tilde should also satisfy Maxwell's equations, right? Maxwell's equations are in fact linear. Okay. So which means that curl of E tilde is minus mu dH tilde over dt, and curl of H tilde is epsilon dE tilde over dt plus sigma E tilde. Okay, so now you may ask what happened to the sources, and the answer to that is the sources are the same for both solutions, right? That's what we say when we want to establish uniqueness. So that's why when you take the difference, they cancel out. Okay, so in fact, E tilde and H tilde satisfy the source-free Maxwell's equations. Okay, so now given this, we can apply Poynting theorem. Volume integral of 1/2 epsilon mod E square plus 1/2 mu mod H tilde square, that tildes, dV. It's the left hand side. You don't have any source term, so you only end up with minus V sigma mod E tilde square dV minus E tilde cross H tilde dot ds. Okay. All right. So now we start applying the conditions we started with, right? So we know tangential or H tangential are known or unique, right? Another way to say that they are known is they're unique, which means that E tilde tangential equal to 0 or H tilde tangential equal to 0, because it's the difference between E1 and E2. And since E1 and E2 are unique, essentially they have to be equal. So E tangential tilde is 0 or H tangential tilde is 0, right? And that makes this whole integral equal to 0. Because one of those terms is always 0, tangential component, and that's what you extract when you take the dot product with ds. Right, so that goes to 0. So what are you left with? You're left with this left-hand side, and this is the right-hand side. Okay? All right, so we need to look at this equation when we're making the rest of the argument. So we know that the right-hand side is always less than or equal to 0, right? Because mod E square is always positive, and you have a negative sign in front of it. So yeah, the right-hand side is less than or equal to 0. Okay? And then we'll apply the second condition, which says that at some t equal to 0, right, the fields everywhere were unique. E tilde and H tilde everywhere were unique, right, which means that E tilde was 0 and H tilde also was 0. And H tilde was also 0, right? Because at t equal to 0, E1 equal to E2 and H1 equal to H2 everywhere. So E tilde is the difference between them, so they are also zeros. Okay, so at t equal to 0, this quantity was 0. So we'll actually maybe label this. So I'll call this the argument. Yeah, the left-hand side, the argument of the integral. Okay. So we have another condition, which is that the argument is 0 at t equal to 0. Okay. And if you also look at this, you have the argument also is always greater than or equal to 0, right? Because again, you have the e tilde square and h tilde square. Okay. So you have that the argument is always greater than or equal to 0 and t greater than or equal to 0. Okay, but this condition says that the right hand side is less than or equal to 0, which means the derivative of the argument is always less than or equal to 0. T greater than or equal to 0. Okay, so we have three conditions that we need to satisfy, and let's see if we can satisfy them. Okay, so at some time t equal to 0, so it's nice, useful to kind of draw a plot. So I'm looking at the value of this argument. So we say that at some time t equal to 0, the argument was 0. Okay, so for t greater than 0, the argument has to be greater than or equal to 0. Okay, but when t becomes greater than 0, for the argument to be greater than or equal to 0, you need a positive derivative, right? And that's not allowed. The argument can only have a negative derivative because of the third condition, which means that starting at 0, it can only remain the same or it can decrease, right? But decrease is also not allowed. So this is not allowed because of the third condition, and this is not allowed because of the second condition. We know that the argument is always greater than or equal to 0, right? So it's not allowed to be greater than 0, it's not allowed to be less than 0, which means that the only value it can take starting at 0 is to remain at 0 for all time. That's the argument, right? So implies e tilde equal to 0 and h tilde equal to 0 for all time. That's the only way for this entire argument to go to 0, right? Both e tilde and h tilde have to be 0 for all time. And that completes the proof. Okay. All right. So let's look at some implications. Okay, what's the first implication? So this is a typical example, which is that if I take a resonant cavity, which is just a closed metallic structure, let's say it's PEC, then I know always that E tangential is 0 on the surface, right? So one of the conditions is always satisfied. But we know inside a PEC that you can have many solutions, right? Just knowing the boundary condition is not enough. So how do we kind of make sense of this possible contradiction, right? You specified the boundary condition, but the field inside, you don't know which mode it is. It can be any of the modes. And the simple resolution to that is that you also need to know the initial condition at some time, t equal to 0, right? And that's what determines the modes inside the PEC. So at some time t equal to 0, if you knew what the field was inside, right? If the field was unique, then that determines what the mode is for all of time. And if you know resonators, essentially the argument goes something like this: at t equal to 0, whatever field distribution you have inside the PEC, that can be decomposed into a set of modes, and all of those modes evolve in a predictable way with time. So at any time t greater than 0, it's just the same combination of those modes, right? But when this cavity becomes very large, when this cavity goes to infinity, then you can have an infinite set of modes inside. And to resolve that, you need to add a small amount of loss on the surface of that cavity, right? And that is essentially like identical to the radiation boundary condition, which we'll see later, right? So at infinity, there cannot be any fields, which means that there has to be some small amount of loss in the medium. Okay? All right. So another implication is that, let's say I have some sources, J comma JS or JM in some medium, and I bound that by some volume V1. And I'm looking at, we have another bounding volume V2, and I'm looking at the space between these two volumes. That's another volume of its own, right? Okay, and now I know from uniqueness that if I specify the field on this surface and on this surface, then that's enough to know what the field is uniquely in this volume here, right? So now what I can do is I can send this off to infinity. And I know when I send that off to infinity from the radiation boundary condition, this has to go to 0, right? So we can essentially say that that field is always known when that surface goes to infinity. We can erase that. Right, so all we are saying is that we only need to know what the surface fields are, E or H, tangential component alone. And if we know that, then the field everywhere else is unique. And this is also something that HFSS uses. So you have your antenna, and there is a bounding box that you apply, which we'll see. Right, so this is your air box. And HFSS essentially calculates what the tangential components of the field are here on this air box. And then from that, you can uniquely calculate what the far field is everywhere, right? So again, uniqueness plays a big role there. Okay, so that's about uniqueness. It's very useful. In some sense, it's obvious that, okay, if I have a given set of sources, I can only have one solution everywhere, right? You can't have more than one solution for a given set of sources. But proving it, we see that it's not really that obvious. You need two more conditions than just saying that, okay, I know the sources, so I know the fields, right? Okay, so the last sort of theorem that we're going to look at is like almost like a corollary to uniqueness theorem. And that's called the field equivalence principle. Equivalence principle. Okay, so what is this saying? Right, so we said, okay, given a set of sources, call this set as sources, and I have another set of fields. Okay, I said that given a set of sources, you can only map to one set of fields. Right, so you can't have from one set of sources, you can't have two sets of fields. That's not allowed. That's what uniqueness established. Right, but it never said something like, doesn't imply the opposite. You can have two sets of sources that give you just one set of fields. Actually, you can have infinite, and we'll see that next. You can have a mapping that's like this, right? Which means that you can have many sets of sources that give you the same fields, but once you know the fields, once you know the sources, you can only get one set of fields from it. Knowing the fields, you cannot know what the sources were that produced that field. At least you cannot know uniquely. Okay, that's an underdetermined problem in some sense. Okay, so the easiest way to prove this is using counter example or an example, but that's the case. So let's do that. Okay, so we again start with this abstract motion of some surface S with the volume V. And we say that we have one set of sources J, another set of sources Jm. Okay, and these are producing fields EH everywhere. E comma H, E comma H. Yeah, obviously E and H are functions of position. Okay, so what I can do is I can take this. So let's actually make a copy of it. Going to let me make a copy or no? Okay, it's good. Right. So if I want to make the fields here 0 on this side of this on the inside of the surface, then I know I need to satisfy a boundary condition which places some currents on the surface. J and Jm. Yes. Right, where Js is given by n hat minus n hat cross E. JMS is given by n hat cross h, right? Because JS is nothing but n hat minus n hat cross E1 minus E2, where E2 is 0. And similarly, JMS is n hat cross H1 minus H2, where H2 is 0, right? So another way to say this is that by placing these surface currents, I can force the fields inside to go to 0 and the fields outside to be the same, right? So the fields on the outside are the same, the tangential fields, that's what the boundary condition is about. So we know that if the fields on the outside, the tangential fields are the same, then the fields everywhere are still the same, everywhere outside the volume, right? That's what we just saw here, which was out here. So what is this saying? This is saying I have two sets of currents. One set is just the J and Jm, and the other set is J and Jm plus Js and Jms, right? Both these sets of currents gave me the same exact fields everywhere outside this volume, right? And of course, the choice of making the fields inside 0 is arbitrary, right? You can make it anything you like. So for example, I can place another copy. Right, so for example, I can make the fields inside E prime and H prime, and then I place currents Js and Jms, where Js is minus n hat cross E minus E prime, and Jms is equal to n hat cross H minus H prime. Right, that still maintains the same fields outside, while the fields inside have changed, and we have the same total field outside, right? So all of these are equivalent from the point of view of the fields outside. The fields inside, of course, are not the same, right? Okay. And you may say, why the fields inside are not the same? The fields inside are not the same because the boundary condition on the inside is not the same. The boundary fields, the tangential fields on the inside have changed. And that's why the fields inside have to change, but the fields outside are the same. Okay. So this is an example proving this corollary, right? That I have multiple sets of sources that are producing the same external fields. Okay, and that's kind of important because we'll use this as well quite a bit. Okay, so those are the theorems. So let's actually put them to use. So far we've developed tools and theorems, Maxwell's equations, but we haven't really solved any problems yet, right? So let's do that. Let's take a simple example and see how all of these tools will be of great use to us in solving antenna and scattering problems. Okay, so let's say I want to find the fields radiated by a horn antenna. So what's a horn antenna? Horn antenna is exactly what it sounds like. So you have some kind of a horn like this. That's not a very good figure. Anyways, just ignore the figure. I can try it again. Okay, let's just say it's a open-ended waveguide like that. Okay, so you have some waveguide, which we'll see much later in the class. Essentially, a waveguide is nothing but a pipe, metallic pipe. In this case, it's a metallic waveguide, but waveguide is a structure that guides waves, that guides electromagnetic waves. So we have here a metallic pipe, rectangular cross section, and that pipe is carrying some field inside it, some wave that's propagating inside it. And we want to see how that field radiates. Okay, so a 2D cross section of this problem looks something like this. Right, let's say I have PEC, PEC. So here, of course, I'm assuming that there are some flanges, right? Some flanges like that. And it's sort of a waveguide that ends on one surface. On the front face, it's PEC everywhere except that hole that is in the middle. That makes this problem a little bit easier. Okay, so you have PEC here, you have PEC here, and then you have some field that's propagating inside. And we'll see later what this field is. We'll solve for that. But for now, just assume it's some electric and magnetic fields. Right, so there's some E comma H that's coming from inside, and you want to see, okay, what is the radiated field? I don't know what this is. Okay, this is obviously a very hard problem because you have all this PEC structure there, and we don't know how to solve this problem. We don't know how to solve Maxwell's equations, basically, right? Okay, so how do you go about this? We can simplify this problem quite a bit using some of the tools that we've developed so far. Okay, so let's do that. So erase this. Okay, so I have a surface here, right, which is this sort of, I guess, this plane, right? Okay. So on that plane, I know what E and H are. So what I can do, so I have some E on this side and H on this side. Right? So what I can do is I can place some currents on this plane. So I place a current JS, another current JMS on that surface, which are equal to minus n hat cross E and n hat cross H. So what does that do? That forces the fields on this side to go to 0. E equal to 0, H equal to 0. Right? So you have some currents and the fields on the other side went to 0, right? To satisfy that boundary condition, which is what we just looked at when we did the field equivalence principle. Right? Okay. So here we have used the field equivalence principle. All right, then what do I do? So then what I can do is that since the fields on this side are 0, right, I can place a PEC there, and that doesn't change the fields on this side. Right, it's not that it doesn't change the fields on the other side, it just doesn't change the fields on this side, right, because they're anyway 0. So I can choose to put a PEC there. This is not a real PEC, of course, it doesn't actually exist, but sort of a mathematical tool or a trick. So now you have PEC here, you have PEC here, and you have PEC here. Okay, but when I put a PEC, now all of this is PEC. And so I can erase this. All of this is PEC. Okay, and I had some currents over there. What happens to the currents, right? When I had the currents and then I put a PEC, which means that the currents were in fact impressed on this problem, right? They're not induced from the PEC, they existed already, and then I put PEC there. So then the currents would have images, right, from image theory. So I have, let me say, I have some current JS, I have some current JMS. And now I can use image theory, right, to get rid of that PEC and then place images. So I have JS and JMS, or the image of JS is the opposite direction, right? Whereas JMS has an image in the same direction. So essentially, JS gets cancelled out and you're left with just JMS. I made a mistake here. So this should be JS and this should be JMS. Did I make the same mistake everywhere? Yeah. So electric current is JS, right? This is also a mistake. Yeah, sorry about that. Where else did I make that mistake? Probably not. Okay, so JS is n hat cross H and JMS is minus n hat cross E. Right? Okay, so the image theory is still correct though. electric field gets cancelled out, electric current gets cancelled out, and magnetic current gets doubled. Right? So what we've done is that what's here. Okay, so what we've done is we have, so this goes there, this goes here. Right, so what we've done is we've taken a waveguide problem, a radiation problem from a waveguide, and we simplified it to nothing but a current suspended in space, magnetic current suspended in space. Right, so this JMS is nothing but 2 times n hat cross H. Keep confusing these two things. It should be minus 2 times cross L. Right, so you've taken waveguide problem and converted it to nothing but a current suspended in free space, and this current is radiating, and all we need to do is we need to find what the radiation is from that current, but it's only valid in this right half space, which is exactly what we wanted. And we wanted to find what the current is in the right half plane or the right half space. And that's a nice trick, and we'll see, we'll use this later to solve aperture problems or radiation from different apertures. And here we've used 2 of the tools we've developed. So we used field equivalence principle, and we also used image theory. Right, so those are the 2 tools. So that's kind of what I wanted to show you, is that the tools and theorems we've developed will be very useful to us in solving Maxwell's equations in different scenarios, right? Okay, so the next thing we'll do is we will actually see how Maxwell's equations are in fact solved, right? So now we are left with actually finding out, let's say for this problem, we need to do 2 things. We need to find what is this field that's coming in, and given a current, how does it radiate? So if I solve those 2 problems, then I know completely what the solution is, right? From this, I can find what E is, and then once I know E, I can find JMS. From JMS, I can find the magnetic and electric, the electromagnetic fields that are radiated from this problem, right? So we'll see, in fact, that this will be solved using Green's functions. We'll see what that is probably in the next or the one after that. And this we'll do much later in the class, which is, waveguide problems. We'll look at that. Okay, so we've essentially basically finished laying down most of the foundation for solving electromagnetic problems. In the next lecture, we'll start solving Maxwell's equations and make things more engineering focused. Okay, so hopefully you're excited about that. Let's quickly recap what we did today. So we started with Poynting theorem, and we showed that from Maxwell's equations, you can derive an expression from which the only valid interpretation for a term E cross H is the amount of power flowing through a given surface, and we call that the Poynting vector. And we said that it's nothing but the power flow per unit area along n hat. And then we developed uniqueness theorem. It says that given a set of sources, the fields are unique under the conditions that the boundary fields are known and the initial fields are known. And we saw several implications of uniqueness, that, given a set of currents, if you know the fields bounding that current, then you know the fields everywhere. And then we also established the field equivalence principle, which says that the reverse is not true. So knowing the fields, you cannot tell what the current distribution was that generated those fields. And in fact, that can help us. And we saw how it can help us, is that, you can generate different set of currents that are maybe easier to solve than the currents you were originally given. And that can be a very useful tool in solving radiation problems. Okay, so with that, we'll stop here, and I'll see you in the next lecture. Thank you. If you have any questions, you can leave them in the comments. Any suggestions or any mistakes I've made, you can point them out in the comments below. If not, thank you. See you.